This is Team Cosmic Snowman, and we worked on NASA's App Development Challenge of 2020. Using the programming languages Python and C#, we created our app in the game engine Unity, and after weeks of researching, coding, troubleshooting, and hard work to complete the task at hand, we are proud to finally present our app, Moonwalker.
The first thing we did to tackle this challenge was create the terrain for Moonwalker out of the data provided. We created an XYZ point cloud based on the latitude, longitude, and height data given to us using the formulas provided. We then imported it into MeshLab, an open source 3D mesh manipulation software, and computed a triangle mesh from the points. We then used MeshLab's processing tools to smooth the mesh.
However, the true purpose of our app isn't just visualizing the moon's south pole, but also the ability to explore it. In Moonwalker, the Artemis crew is represented by this futuristic rover that we modeled using Autodesk Fusion 360 and Autodesk Inventor. It's through this rover that the player is allowed to interact with this environment. Starting at the landing site represented by a small lander, players are allowed to travel across the lunar south pole as they please, using the controls W, A, S, and D to move, space to brake, and B for parking brake.
In our attempts to make the moon itself as realistic as possible, we first added our own texture through the Terrain's Assets feature in Unity to mimic the created surface of the moon. The lighting was adjusted so that the sunlight would strike the surface at a low angle as it does on the lunar south pole. Since this left a large crater in darkness, we added headlights to the rover so that the player would not lose visibility. This visibility was provided by the implementation of 3 cameras totaling to 4 camera angles, each enhancing the user experience.
But while exploration is encouraged, the Artemis crew in reality would require a much more straightforward path to reach their end destination. We used Unity's NavMesh generation tool to create a path that the player can follow, as well as custom NavMesh agents to deal with the different optimizations. These options include a path of shortest distance while still remaining under 15 degrees of slope, as well as a different path that stays under 10 degrees. Along the way are checkpoints that we modeled for the Artemis crew to communicate back to Earth as they travel, optimized so that each path has individual checkpoints that have inherently smaller azimuth angles to the horizon than to Earth. These checkpoints are at equal distances from each other to keep communication consistent throughout the journey until the player reaches the American flag standing at the end, paying homage to the Apollo 11 mission.
We also visualize the data in other ways as well. Using a diverse set of Python libraries such as Matplotlib and GDAL, we were able to create a representation of the height and slope data in heat map form. By using techniques like downsampling, we were able to visualize the data despite technological and monetary constraints as we created our own software to accurately portray the overwhelming amount of data given to us.
And besides the option to toggle between cameras, Moonwalker offers other interactive data to the user as well. A speedometer at the bottom shows the acceleration of the rover as the user brakes or speeds up. Using MATLAB, we derived the necessary equations for ascertaining the latitude, longitude, and height given XYZ coordinates. From this data, we were also able to provide real-time calculations to provide the user with the azimuth and elevation angles of their position, giving the user the fullest experience possible.
While making Moonwalker, we ran across a number of technical difficulties, physical and monetary limitations, and the challenge of learning new techniques and dealing with large data.
For example, when we imported the XYZ file of the visualized data into MeshLab, we found that it only created a half sphere with 2 mounds on the surface. It was only after much analysis that we found that Python's trigonometric functions use radians. We switched to degrees and finally brought up an accurate visual of the terrain within minutes. Smoothing the terrain also brought up both hardware and software limitations, as the mesh processing programs we used were not made to handle tens of millions of triangles. The ones that could used up extreme amounts of computing resources. Therefore, we were limited on how much we could process the math.
Other than these silly mistakes, our biggest learning curve during the challenge was definitely Unity and its C# scripts. Both of these were new to all members of the team, so a large amount of our time was not spent creating, but instead learning. Stable camera movement was a key component of the app we initially struggled with. We first attempted to mimic real-life optical image stabilization techniques in order to keep the camera stable while the rover was not. However, further research guided us into using the Unity engine terrain, which helped eliminate the unevenness altogether.
In the end, however, we found communication to be the largest hurdle we faced as we took on this challenge during a global pandemic. As a team, it was harder to convey our thoughts and ideas through virtual meetings. While we were able to work around this, something that was harder to bypass was how we did not have the opportunities we would normally have to reach out to local experts in person. Setting up virtual meets proved to be uneventful as well. However, with the internet at our fingertips, we reached out to the Unity community itself for assistance.
The many forums and servers composed of Unity experts and professionals were our saving grace in this challenge. Whenever we had a question or were stumped on Unity's many tools, the community had an answer, whether it be a helpful brainstorming session or just a redirection to older forums of people who had faced similar problems and had found solutions.
In this world of struggling industries, the game development community has still continued to thrive and grow, and we hope to show our gratitude to the Unity Society both past and present by becoming its future. We'll be sharing Moonwalker with the online community and make our GitHub public to help others the way others have helped us. We also plan on spreading this app throughout our school district for people to download and discover on their own, aiming to educate and inspire the younger generations to reach for the stars and beyond. After all, with Moonwalker, anyone can take that one small step for man and one giant leap for mankind. Thank you.